Okay, 401. Yes. Sorry, I'm a minute late. Welcome back to your favorite class. Yes. Okay. Manufacturing document due today. Yes. Finally off your shoulders. Okay. Hope you voted today. Or you got your absentee ballot in. I just showed mine. I turned it in September 27th. It was over a month ago. All right. Hopefully you guys voted also. Homework's due on Thursday. That's really the only announcement that we have here. All right. Yeah, blame Preston for this meme. All right. So using the whole grading scale, 10 to 96, he still has 14 points of leeway. So keep that in mind. Still has 14% more wiggle room. All right. So as they say, I was too tired. Oh, Kevin, I'm disappointed. As they say in Mulan, let's get down to business. All right. Let me get rid of this. Goodbye. And let's remind ourselves where we were. All right. So just kind of recapping here quickly. We're going to cover 4 theories for thin lamina strength theory, the Department of Redundancy Department. Okay. 4 theories that we're going to cover. Max stress theory, we sort of talked about last time. We're going to have max strain theory we'll talk about today, the Sci-Hill theory, and the Sciwoo theory. All right, so those are the 4 main ones that we have for this course. We talked about the maximum stress theory, and basically you're calculating stresses in the principal material directions given some off-axis loading using stress transformations, then comparing the stresses that you calculate in principal directions to various failure strengths. If you exceed any of the stresses that would cause failure in that direction, you fail. So the idea is if you're moving along these sort of directions here, you could run into a boundary. You run into a boundary, that's your kind of failure envelope. So you hit any of those boundaries, you're gonna fail. All right, so this is just looking at stress in a single direction. If it exceeds that value, you're gonna fail. Not a very complicated theory, but it's a good place. We talked about then how the strength of these lamina vary as you're changing the loading direction with respect to the fiber direction. So if you're like only loading in one particular direction, sigma x, only sort of this like unidirectional loading, and then you're changing how the fibers are aligned, what's going to happen? Well, we talked about sort of at small values of theta, you're going to be loading mostly in the one direction. At large values of theta, mostly in the two direction. And if you're kind of somewhere in between, you've got a combination, kind of loading mostly in shear. Right? So the idea is as you're sort of aligning the direction of loading with the fiber direction, you're kind of induce different stresses in different directions and cause failure in different directions at different sort of like angular positions. And so your angular alignment with the direction of your loading, if it changes, you can anticipate some failure stress in this sort of like X direction. So that's what we're kind of trying to plot with this particular graph here, is looking at as you vary the angle of the fiber with the direction of loading, so the angle between the sigma x and let's say the one direction, you're going to have significant changes in your strength. That's because as you start to load off of the fiber direction, your strength is going to go way down, especially as you begin loading along this like two direction mostly because that two direction is just so weak. All right. Okay. So that's about where we left off. And now we'll move on to new material, which is the next theory, and that is max strain theory. Will look very similar to the maximum stress theory. This one isn't used nearly as often. All right. So it's very similar to max stress theory. But the idea here now is that if the strain exceeds a certain value in any particular direction, you fail. So the idea here is more or less the same, is that we want to basically get the strains in those principal material directions and compare the strain that we have in those principal direction to some principal strain that might cause failure. So in math speak, mathematically, we'd have if epsilon 1 is greater than, or we'll say greater than or equal to, that which would cause failure in the one direction in tension, then you would fail. If epsilon 1 is less than or equal to that which would cause failure in the one direction in compression, you fail. Usually you put a negative sign because the negative sign is usually not inherent in the strain value. If your strain in the two direction is greater than that which would cause failure, or if your strain in the two direction is less than that which would cause failure in compression, or if your strain in 6, usually we call this gamma 6, absolute value is greater than or equal to that which would cause failure in the 6th direction. If any of these are met, you fail. Okay, so let's define some of these things in terms of what we know about the composite. Remember, we know things like the strength in the one direction in tension, the strength in the two direction in tension. So let's can rewrite strain to failure in terms of stresses to failure and material properties. So what I mean by that is, you know that your strain to failure in the one direction in tension is going to be equal to the failure strength in the one direction in tension divided by the modulus of the composite in the one direction, for example. Let's leave the negative sign out of here. Strain to failure in the one direction in compression is whatever that failure strength is in the one direction in compression divided by the modulus of the composite. And you could do this for all of these guys. Strain in the two direction, which would cause failure. This is F2T over the modulus of the composite in the two direction. Strain to failure in the two direction in compression is just the failure strength in the two direction in compression divided by the modulus in the two direction. And then obviously the strain to failure in the sixth direction is just going to be this F6 over G12. Okay, so remember all these, we talked about how to calculate these in your micromechanical strength theory portion of the course. Remember, we talked about how to calculate all those guys. All right. We also talked about how to calculate these guys in the very beginning of the course using Halp and Psi equations and whatnot. Okay. All right. So these more or less are the failure strains. And we want to compare these failure strains against the current strain that's on the piece. Right? All right. So these are kind of like our failure conditions up here. We want to compare those two. What are the strains that we actually have on the piece? Well, we want strain on piece in terms of the stresses that we know. Okay, so that requires a Hooke's law. All right, so the current strains, that would be like, what is the strain in the one direction? You're gonna sing me a song? One Direction song? Lucas does tomorrow, even though we don't have class tomorrow. Clever, clever. All right, this is 2D Hooke's law. We're gonna, thin structure, plane stress. We're kind of assuming. So this is 2D Hooke's law. 1 on E1 multiplied by stress in the one direction minus nu 1, 2 stress in the two direction. Strain in 2 is the current stress in the two direction minus nu 1, 2 times the current strain and the stress in the one direction. And finally, your shear strain is whatever the current stress is in the 6th direction. Wow, that was a crazy sigma. Divided by modulus 1, 2. Okay, so these are the current strains on the piece. Okay, so we're going to compare these current strains to what we saw above, which was the strains that would cause failure. But we're going to write this in terms of stresses because the stresses are more or less like what we know. We know failure stresses from our calculations from last time. So it's just a little bit easier to write everything in terms of the stresses, even though this is an analysis of the strain. We're kind of transforming the strain into stress through Hooke's law and rewriting. So finally, all together, we have the following. We fail if any of the following conditions are met. So if epsilon 1 is greater than 0, so we have some positive strain in the one direction, then we fail if sigma 1 minus nu 1, 2 sigma 2 is greater than F1T. This is like the current state of strain, except I've taken out the modulus bit. Like that which would cause failure, except I've sort of taken out the modulus. Remember that both of these sides, when we write them in terms of strains, are both like divided by E1, right? So I've just kind of gotten rid of that. Okay. And I'm being very specific here in saying that if your strain is greater than 0, meaning you have tensile strain in the one direction. If you have a compressive strain, you still have the same sort of equation. But here, this is going to fail if it's less than negative F1C, say less than or equal to. All right, so this is again like the current state of strain on the piece compared to quote unquote the strain that would cause failure. Here again, we've just gotten rid of the 1 on E1 for both sides. Similar idea for strain in the 2. If we have positive strain in the 2 direction, then if this is greater than F2T, or the situation where you have compressive strain, this is your condition. And lastly, the magnitude of your shear stress in plane is greater than that which would cause failure, you fail. All right, we might want to plot the failure envelope for this particular situation. Question? What's that? Speak louder. Right, in the notes I'm writing the safety condition. Here I'm writing the failure condition. I think it's a little easier to write in terms of failure. So I've adapted on the fly. Yeah, in the notes it's different because I've written the safety condition in the notes, but I've written the failure condition here on this white pad. So if you're looking at the PowerPoint and thinking I made a mistake, I did not make a mistake. Okay. So I'm going to plot these four. In the sigma 1, sigma 2 space. That is this failure envelope that we've talked about before, plotted in the state of sort of principal material direction stress. Okay, so let's try to maybe make ourselves a nice big graph here. Here's the one direction, two direction. Lucas is texting his mother. You are really? That's funny. He was like trying to hide it under the table, be all sneaky. I see what you're doing over there. His face is so red right now. You should see it. Oh man. All right, so we're still going to have some of these critical values. All right, like if we don't have any stress in the one direction, then we're just going to run into F2T here. Or if we're loading in the other direction, negative F2C. All right, same thing in our kind of one direction over here. We'll run into F1T. And over here, we'll run into like negative F1C. So those boundaries are still sort of in effect, right? Those are pretty easy to identify with some of our equations above, right? So if you have sigma 1 equal to 0, then you're going to run into F2T and F2C. If you have sigma 2 equal to 0, you're going to run into F1T and F1C, respectively, depending on if you have tension or compression. But what's more interesting now is what happens when we have combined loadings for like both contributions of sigma 1 and sigma 2. All right. So let's plot some of these equations here. The first one I want to plot is kind of the first one on the list here, is this general equation, sigma 1 minus nu 1, 2, sigma 2, equal to F1T. If you want to just think about writing this in like slope-intercept form, your x variable is like sigma 1. Remember, this is like your x variable. This is like your x variable. So you could rearrange this to like slope-intercept form where you divide everything by, nu 1, 2 and rearrange so that you're solving for sigma 2. You could do something like that. But I think you guys kind of passed algebra. Otherwise, you wouldn't be in this class. So good for you guys. You see an equation that looks something like this. Okay, so this is the line that is defined by sigma 1 minus nu 1, 2, sigma 2 equals F1T. If we're left of that line, we're safe. If we're right of that line, we fail. Similar idea on the backside. If we're looking at F1C, I'll have a similar looking sort of equation here. This equation, sigma 1 minus nu 1, 2, sigma 2 F2C. We can continue on with our remaining equations. I'm not going to write them all in here, but you get the general idea. There's sort of this like slight upward slope to that guy. Similarly down here, sort of this like slightly upward slope. Right. That would be like equations 3 and 4 on that list up there. So the point is you get this failure envelope that kind of looks like a parallelogram. Is that the right word? Rhombus? It's not a rhombus, is it? I don't know. I didn't pass kindergarten, so maybe they should strip me of my PhD. Anyway, looks something like this. Okay, we're here if you're inside this region. I don't like the black. It's not pretty enough. I need more color. Let's pick blue today for obvious reasons. Oh man, I don't know how many people got that or not. Safe. Say. Safe. So basically what happens here with this maximum strain theory is that you just have like a slightly tilted, with your max stress condition, it was just like this rectangular piece. And now you're basically tilting your rectangle to get you this rhombus based on the Poisson's ratios of your materials. So you just see a slightly, I don't know, deformed rectangle here. It's a parallelogram. Okay, so that's your max strain theory. Probably not going to ask you much about that on any homework or test, just because that theory is really not used that often. Maximum stress theory is common because it's very simple. Maximum strain theory, not all that common in practice. But okay, that's the idea. Process is more or less the same as max stress theory. You determine what the stresses are in principal directions, compare it to that which would cause failure, but here using the maximum strain theory. Do I have a question? I also love the blue man group. Obvious reasons. Okay. Okay, let's get into the next theory. Now we're getting into the energy-based theories. And the next on our list is the Sci-Hill theory. All right. And this one is akin to von Mises. So similar to von Mises for isotropic materials. So remember what your von Mises criteria is. So this is von Mises in 2D. Remember something like sigma 1 squared minus sigma 1, sigma 2 plus sigma 2 squared. If this is greater than or equal to that which would cause yield squared, you fail. Yes? Yes. Okay, if you rearrange this, you divide by sigma naught squared. That division symbol, rarely used. All right, but let's say that you divide this entire expression by sigma 0 squared. You're going to end up with the following. So this is just rewriting the von Mises failure criteria. The idea here is you're more or less like imagining that the amount of stress that your piece can hold, or the amount that it has available for it before it fails, is like 100%. Okay? And each little bit of stress that you add, divide that stress by that which would cause yield. Once you've broken on 100%, you've failed. So you have combinations of sigma 1, combinations coming from sigma 2, etc. So the idea here is that, like, okay, let's say I have some stress in the one direction. I normalize it by that which would cause yield, and I get some percentage. All right, so, maybe this is giving me 90%. Okay, so I'm pretty close to failure, but not quite. And then maybe later on, I have some biaxial stress, so I have some sigma 2 divided by that which would cause failure. And now that additional amount has given me past the 100% that I can have, and now I have failed. So that's kind of the idea that people rolled with the Sci-Hill criteria. So here, each one of the stresses is basically being normalized by the yield stress. By one value, and that's like sigma 0. And once we exceed 100% of materials capacity, we fail. We have a very similar idea with the Sci-Hill theory, right? Except the Sci-Hill theory, you're not normalizing sigma 1 and sigma 2 by the same value. You normalize sigma 1 and sigma 2 by their respective values which would cause failure in that direction. So this is a very similar process for Sci-Hill. You have to think about like 100% of the capacity of the material to hold load before it fails. And whatever load you add, normalize that by that load which would cause failure in that direction. And once the individual contributions of all the bits exceeds 100% of the capacity of the piece, you fail. So similar idea in Sci-Hill. Okay. Except now, normalize each principal stress value by the failure stress in that direction. For isotropic materials, you just normalize by sigma yield in every direction because the material is isotropic, right? For Sci-Hill, you normalize by the failure stress in that particular direction. So the result is the following. It says that sigma 1 divided by F1 squared plus sigma 2 divided by F2 squared plus sigma 6 divided by F6 squared. And then we have this interaction term, which also occurs in your von Mises stress, which we'll see here, minus sigma 1, sigma 2 over F1 squared. If this is greater than or equal to 1, you fail. So this is your Sci-Hill theory. Very similar in flavor to von Mises. Tastes like chicken, just like everything else. So we see here each one of these pieces being normalized by its stress that would cause failure. So here, like the stress in the one direction being normalized by the stress that would cause failure in the one direction. Here, whatever stress you have in the two direction normalized by the stress that would cause failure in the two direction, et cetera, et cetera, et cetera. So as long as that stress isn't exceeding that which would cause failure, you're going to have less than one contribution from each of those guys. Now, what you notice here is that I haven't specified F1T or F1C. I haven't specified F2T or F2C. F6 is kind of irrelevant, but the point is that you need to specify F1 as F1T or F2 as F2T. Similarly, you need to specify F2 as F2T or F2C. And that's pretty straightforward. The way that we do that is if F1 is greater than 0, use F1T. If F1 is less than 0, use F1C. If F2 greater than 0, use F2T. If F2 is less than 0, meaning you're in, why am I writing F? These should all be sigma. Sorry about that. Okay. I think this idea is pretty straightforward. If you know that your stress in the one direction is in tension, normalized by the failure stress that would cause tension. If you know that your stress in the one direction is in compression, normalized by the failure strength that would cause compression. All right. Same thing over here for these two directions. Okay. So there you go. Now, what does that failure envelope actually look like? This is a very strange sort of thing to actually compute. And we know that as you move from like one quadrant to the next, if you're plotting in like the sigma 1, sigma 2 space, you're going to have changing values of those denominators. So I'll just put up the failure envelope here. And this is also available in the notes if you want to take a look. I also have MATLAB. Rawr. Just proving that I can also do MATLAB too. So here's your kind of, if you're inside of here, obviously, you're safe. This specific graph is for an E-glass epoxy composite. With a volume fraction 55%. So still out here we have like F1T. Still over here we have like F1C. Our critical values are still kind of present, right? F2T down here, F2C, etc. So we still have those like critical values that we're running into at those edges, right? And we see these sort of like jump discontinuities which exist. I've kind of like highlighted them a little bit here, kind of on like the left and the right hand sides of these two different graphs. And that's because as you kind of cross over from like the left-hand side of the figure, which is here, to like the right-hand side of the figure, which is over here, you're changing what values of F1 you're using. Okay, so over here, your equation uses F1C. And on this side, this right hemisphere, your equation uses F1T. Okay? And that's separated by like this hemisphere here, which is like this y-axis. So you see some discontinuities of this equation as you jump from like the left-hand side to the right-hand side. And similarly, as you jump from like the top here to the bottom, like above here, you're using F2T. Below here, you're using F2C in your equation, etc. So you see these like strange jump discontinuities, which kind of make this equation look a little strange at these axis jumps. Okay, so that's your Sci-Hill theory. Last one we're going to talk about, presented without derivation. And that one's a little bit crazy. And it's got similar flavors to Sci-Hill, and that's an energy-based theory. But this one's called the Sciwoo theory. All right. I'm not going to really drive it here. Just say without derivation. We fail if. It's a bit of a long one, so buckle up. Here we have these strange terms. Here's an F1, sigma 1, plus F2, sigma 2, plus F11, sigma 1 squared, plus F22, sigma 2 squared, plus F66, sigma 6 squared, plus 2, F12, sigma 1, sigma 2. If this is greater than or equal to 1, you fail. So I know you're all begging me. What is F1, F2, etc.? Right? This is another energy-based theme. It's got very similar ideas where these F terms are again going to sort of be like normalizing the stresses in the various directions. But here we've included like lower and higher order energy terms. So it makes this theory probably the most accurate of all of them what we've talked about. Here's 1 on F1T minus 1 on F1C. F2, 1 on F2T minus 1 on F2C. F6 on F6 squared. Sorry, this should be F66. F11. 1 on F1T times F1C. And my last one, which is a little bit weird. -1/2 square root f11 f22. And all these above. You want to take F1C and F2C as positive values. So I know sometimes we talk about in compression, you use negative values. But in the equations above, use F1C and F2C as positive. Complicated. But this is just more or less, it's very similar to the von Mises theory, very, very similar to Sci-Hill. Except you're not normalizing against like one particular stress. You're normalizing versus against this strange combination of failure stresses in the various directions for tension and compression. So it's a little different, but the spirit is still there. All right, your failure envelope. This one's actually quite nice because failure envelope. Oh man, spelling is hard. So this here is just a elliptical equation, believe it or not. Well, an ellipsoid. It's actually a three-dimensional equation. But if you plot it in 2D, you'll see an ellipse. So here in the sigma 1, sigma 2 space, you'll have the following. This. This is kind of right from your book. This is E-glass epoxy. And we'll make a note here that this K that they're showing here is an attempt to incorporate how the shear stress might affect the size of this particular ellipse. So here, K is sigma 6 on F6. So this gives an indication of how much shear is present inside of the piece. If no shear stress is present, you have this K equals 0 value. And if you have shear stress on your piece, which is equal to the shear stress which would cause failure, you're at this K equal 1 sort of contour line. And we would see then that if we have no stress in the 1-2 direction, that we'd be right on the failure line for failing in shear. So again, like this value here is F2T, this value here, F1T, etc., etc., etc. You get the point. Okay. Last thing I'll say is working through conservative design. So just like in 3005, when you're looking at max stress theory, von Mises theory, Tresca criteria, we know that each one of those three different criteria had various levels of conservation. Okay. Generally, the Tresca criteria was the most conservative, and generally the max stress theory is least conservative. Right? We have similar ideas here. We have some stresses that are some theories that are quite conservative and some that are not conservative. So when you're sort of attacking or thinking about design, you might want to consider the conservation of each one of the theories. So you can think about the conservation of each of the theories by, let's say, looking at their relative failure envelopes given some certain composite that you're working with. Right? So here's an example with carbon epoxy that I took from your book. I stole it. So this is from your notes. Okay. And so here we see the relative conservation of some of these theories. All right, your max stress theory, that's the one we usually start with. It's just kind of this box here. Bam. All right. That one's kind of a good catch-all. All right. If you want a more conservative theory, then you want to pick a theory that's sort of inside of that. And both of our Psi-Hill and our max strain theory are close to that. But generally, here we see like this dashed line here. This is your Psi-Hill theory. Okay. This would be like most conservative. All right. It's your Psi-Hill. This is most conservative. Generally, but not always the least conservative, is the Sciwoo theory. So here's your Sciwoo theory. And here we got this like big old thing, like all the way out here in this compressive area. Though it like comes on the inside of Psi-Hill in some points. So it just kind of depends which one's going to be most or least conservative. But in general, if you sort of had to rank them, maybe your most conservative would be Psi-Hill. Then next, max strain. Next, max stress. So these are about the same. And then finally, Sciwoo is least. Okay, and this is always important in consideration of design, you know? Did I get that backwards? Yeah, no, this is correct. Okay, I was just double guessing myself for a second. Yeah, this is correct. Okay, that's gonna do it for today. 450. Why does it look like I hand drew over the plot? But I did hand draw over the plot. Oh, was that like this one? Oh, no, I didn't hand draw over that, except all those notes that are right there. Okay, that's it for today. We'll see you on Thursday.